Welcome back. In this module, we will discuss the short-term behavior of DTMCs. So far, we have studied long-term behavior, that is, if you start off a Markov chain in some state and run it for a very long time, does it converge to a stationary distribution or not after a long time. That is a different consideration from what we are going to consider now, which is short-term or transient behavior. So, the questions here are like, if you start at a transient state, all right, what is the how long would it be before you get absorbed into a recurrent class, for example. If there are multiple recurrent classes, what is the probability that you get absorbed into one of these recurrent classes, right. So, these are the kind of questions that we would wish to answer in this particular module, all right. So, let us consider a transient state I. Okay. So, this is the starting state. So, you say that and say x naught equals I, right. So, you are starting at a transient state I. Okay. Let us say you are starting at some transient state I at time equal to 0. Okay. There are many states, and let us say there are some, this is recurrent, this is one recurrent class R1, this is some recurrent class R2, with a whole bunch of states inside them, right. So, there will be some transitions inside the transient class, and there may be some into the recurrent class 1, some may be into the recurrent class 2, and so on, right. Now, starting at I, the questions of interest will be as follows, right. What is the probability that starting at this transient state I, we get absorbed into the recurrent class R2, for example, right, or R1, does not matter. So, you could have a number of transient classes and a number of recurrent classes, and let us say you are starting at one of those transient states, and I want to look at the probability of getting absorbed in a particular recurrent class, right. Of course, you are going to, with probability 1, if you start at a transient state, you are guaranteed that with probability 1 you will enter one of the recurrent classes, right, but you do not know which one you will enter, right. You may enter R1 on one run of the Markov chain and then stay in R1. In a different run of a Markov chain, you could start at I and enter R2 and stay in R2, right. So, what is the probability that you start in I and enter say R2, the recurrent class R2, right. This is a question of interest. Another question of interest is how long before you get captured, right. What is the expected time until a recurrent state is entered? These are the kind of questions we want to discuss. This is what I mean by short-term behavior. See, long-term behavior, we know that in geometrically fast we are going to get out of the transient class, but I want to precisely characterize which, with what probability do I go to which recurrent class, and what is the expected time to get into that recurrent class. Okay, these are the kind of questions I want to talk about. It is easiest to discuss these sort of questions using examples and then generalizing. Okay. So, I am just going to consider an example of this Markov chain. Let us say I have a 5 state Markov chain in which state 1 is absorbing. So, if you are in state 1, you are always in state 1, and then the other transition probabilities are as follows: 0.2, 0.3, 0.1, 0.5, 0.3, and say this is 1, this is 0.7, and that is 0.3, this is 0.2. So, I have just taken an example. Okay, this is a 5-state DTMC with the transition probabilities given. Okay. If you look at these states, it is very clear immediately that state 1 is a recurrent class by itself, right. And if you look at the states 4 and 5, once you are in states 4 and 5, you can go from 4 to 5 and you can go from 5 to 4, right, but you cannot get out from this 4 5, right. Once you are in one of these 4 or 5, you will always remain in 4 or 5, which means that this 4 and 5 is another recurrent class R2. Okay. And if you look at this 2 and 3, you can go from 3 to 4 or 3 to 5, but you can never come back from 4 to 3 or 5 to 3, right. Similarly, you can go from 2 to 1, but you can never come back from 1 to 2, right. So, that means that these states are transient, 2 and 3 are transient, right. Now, the question is, starting at, let us say starting at x naught equal to 2, what is the probability of getting absorbed? What is getting absorbed? Meaning you start at 2 and you reach this R2 class, getting absorbed in R2, right. So, you get into one of these 4 or 5 and you remain there, right. So, you have to get captured either in R2 or get absorbed in R2 or R1, right. I am asking, starting at state 2, what is the probability that you get absorbed in this recurrent class R2, or starting at state 3 for that matter, right. So, this can be calculated as follows. Okay. Let A2 and A3 probability of getting absorbed in R2 starting at state 2 or 3 respectively. Okay. So, now if you notice, once I reach state 4 or state 5 in R2, I do not care, I am going to remain in state 4 or 5, right. So, if I start in state 2 and eventually end up in state 4 or state 5, I do not care, right. I am going to remain in the recurrent class. So, what I am going to do is to draw a modified Markov chain in which the recurrent class R2 is converted to a single state which is absorbing, alright. So, I am going to keep this part of the Markov chain the same. So, 1, 2, 3, everything here is the same. All these probabilities are the same, 0.1, 0.2, except I am going to call a new state 6, which is an absorbing state. From 3, what is the probability that I go to either 4 or 5? It is 0.8, right, it is 0.5 plus 0.3, right. So, if I am at 3, the probability of going to one of this 4 or 5 is 0.8. Likewise, if I am in state 2, the probability of going to state 6 is 0.1. Okay. And once I am in state 6, I am going to be in state 6 forever. Sorry, I got this wrong. This is 0.4, otherwise they won't add up to 1, right. Now, here I want to ask, what is the probability that starting at state 2, I get absorbed in state 6. I have to get absorbed in either state 1 or state 6. Now, what is the probability that I get absorbed in state 6? Okay. Now this can be calculated using the following set of equations. Okay, this is by using the theorem of total probability. Okay, A6 is equal to 1, right, because if I start at 6 I am going to get absorbed at state 6 with probability 1, and A1 if I start at state 1 I am not going to get absorbed in state 6. So, I will say A1 is equal to 0, right. Now, I can write A2 is equal to 0.2 times A1 plus 0.3 times A2 plus 0.4 times A3 plus 0.1 times A6. And then for A3 I am going to write A3, the probability that I start at 3 and get captured at 6 eventually is equal to 0.2 times A2 plus 0.8 times A6 that is it, right. Now, if you solve, so this A6 is of course equal to 1 and A1 is equal to 0, right. If you just go ahead and solve this, you will get A2 is equal to 21 on 31 and A3 is equal to 29 on 31. So, you get something, right. The bottom line is that you can write out these equations and calculate the probability that you get captured in this recurrent state R2, which I have just collapsed into one absorbing state, right. More generally, I can write the following. Let us say you have an absorbing state, let me just say there is one absorbing state, there is an absorbing state S, which could be a collapsed version of a recurrent class like I did above, right, and start at some I, right. Then you can write out the following equation. As is equal to 1. So, if you start at S, you are going to get absorbed in S with probability 1. Ai is equal to 0 for I not equal to S, I absorbing, like we had above if A1 was 0, right. If you start at an absorbing state which is not your absorbing state S, you are going to remain in that I, right. So, you are not going to get absorbed in S. And then finally, for all transient I, you have the equation sum over j equals 1 to m Pij Aj for I transient. Okay. So, these are the equations governing, if you start at I, what is the probability that you get absorbed into the particular absorbing state S. Okay. This is the set of equations you have to solve. This is just by the theorem of total probability, and it can be shown that this system of equations always has a unique solution. Okay. I am not going to prove uniqueness here. So, this general discussion in this lecture can be found in the book of Sithiklis and Bertsikas, which is an undergraduate text on probability, and this is section 7.4. Right. So, this entire topic is covered in this particular book. Next, we move on to talking about this absorption times, right, expected time to absorption, or heating times, expected heating times, right, they are variously known. So, you start from I, it is a transient state, what is the expected time to absorption? To a recurrent state. Let mu I be defined as expected number of transitions until absorption given x naught equals I. Okay, that is nothing but expected recurrent given x naught equals I. So, these equation mu i's can be shown to satisfy a different set of system of equations using the theorem of total expectations. In fact, we can show that this mu I satisfy mu equal to 0 for all recurrent I and mu I is equal to 1 plus sum over j equals 1 to m p I j mu j for all transient I. Okay. This is the system of equations that one needs to solve. Okay. Intuitively, this mu I is the expected number of transition until absorption. This is the set of equations that we have to solve for mu i's. Intuitively, mu I is the expected number of transitions until absorption into a recurrent class, right. So, mu I is 0 for all recurrent I and mu I is equal to 1 plus sum over p I j mu j, right. So, this interpretation of this equation is that you start at I, you take a step, you go to state j and from state j you have this expected time to absorption is mu j, right, and the probability of going to j is of course p I j, right. So, this is just the total theorem of total expectations. Now, this also has a unique solution. Okay. This also can be shown, I am not bothering to show it. This is the system of equations to solve for the expected time for absorption. To show you an example from the book by Bertziklas and Tsitsiklis, you consider this Markov chain. So, 4 state Markov chain. In state 1 and in state 4 there are 2 spiders, okay, and there is a fly that keeps jumping around between these states. Okay. So, from state 2 to state 3, so these are the jumping probabilities of the fly. So, the fly jumps forward or backward with probability 0.3 and stays in the same state with probability 0.4, but if it jumps forward with probability 0.3 from state 3 and it reaches state 4, then the spider will eat the fly. Okay. In that case, the fly will not come back. Okay. Likewise, state 1 also, if the fly jumps from state 2 to state 1, the fly will be eaten by the spider, and so in that sense state 1 is absorbing. All right. Suppose, so here let us say you are starting at state 2, right. Starting at state 2, what is the expected time until the fly gets eaten by the spider? So, we have mu 1 is equal to mu 4 is equal to 0, right, because they are recurrent, and for transient states 2 and 3 are stand transient states, you have the equation mu 2 is equal to 1 plus, you are starting at 2. So, and with probability 0.3 you are going to state 3. So, 0.3 mu 3 plus 0.4 mu 2, and likewise mu 3 is equal to 1 plus 0.3 mu 2 plus 0.4 mu 3, right. And if you solve the system of equations, you will get mu 1, so mu 3 is equal to mu 2 is equal to 10 upon 3, all right. So, the expected, so whether the fly starts at state 2 or state 3, the expected number of transitions until the fly is eaten by a spider is 10 over 3, okay. So, this is an example from the book by Bertsikas and Sisakoulas. Now, this is basically you start a transient state. What I have talked about is started a transient state and you calculate the expected time to absorption, right. Now, we can also talk about expected first passage times. Expected first passage time is the expected time that you take to reach some state I, given that you started in so expected time until you reach a state S, given that you started in state I, okay. This state S does not have to be absorbing, or there is no need like there should be a spider there that we can't get out of, okay. So, let us say there is some generic state S, okay, you are starting I and you want to calculate the expected time until the first time you reach S, okay. Now, what you can do is you can make the state S an absorbing state, even if in the original Markov chain, if state S need not be absorbing, you are just looking at the expected first passage time, right. So, what you do is you make that state S an absorbing state and you calculate the expected time to absorption, right. Then you can calculate the expected time to go from I to S, okay. Expected first passage time or mean first passage time is the, let us call this Ti, let S be any state not necessarily absorbing and x naught equals I, okay. Ti is defined as the expected min n greater than or equal to 0 such that x n equals S. So, this is the first time you reach S given x naught equals I, okay. So, in this we are not saying necessarily that S is an absorbing state, but we are only interested in the first time, the first passage to S starting at I, right. So, then what you can do is you can make S an absorbing state, okay. So, in this case transitions out of S are irrelevant, right. So, make S an absorbing state and then you apply the formula that we derived for the mu's above. So, essentially we make, how do you make S an absorbing state? You make PSS is equal to 1, right, and then you apply the formula above, okay. So, you are given some Markov chain, right, and you are looking at the expected time until I first reach a state S, right, starting at I. So, what I do is I modify the Markov chain to make PSS is equal to 1 and then apply the formula derived above for this fly example, the mu formula, and you get the expected first passage time. Also want to mention expected mean recurrence time of state S is, what is the expected mean recurrence time of state S? It is defined as, TSS is defined as expected number of transitions such that xn equals S given x naught equals S. Okay. So, you are starting at some state S, what is the first time after that you return back to S, okay, and what is the expectation of such a time, right. So, this is simply the first passage time, not starting at I, but this starting at state S itself, okay. So, how do we calculate TSS? Okay, we can obtain TSS once we have the first passage times Ti above using the equation TSS is equal to 1 plus. So, you are starting at S, right. See, now you cannot afford to make S an absorbing state, right. So, the earlier we could say I am starting at I want to calculate the mean passage time to some other state S. I could just forget about transitions out of S and make S a absorbing state, right, and then I could calculate Ti using the formula above. But if S, you are starting at S, right, then you have to transition out of S into some other state and then come back to S, right. So, now you cannot afford to make S an absorbing state. So, what you do is to calculate the expected mean recurrence time of state S, you first calculate the Ti's, which are the first passage time starting at I, right. Then you say from S I have to go to some I and then come back to S, right. So, from S I have to go to I, the probability of that is PSI, and I have the mean first passage time from I to S, Ti, right. So, this is just Ij equal to 1 to m. Of course, I can be S itself, right. So, this is the equation. So, if you know Ti you know before from above, right. So, how would you calculate Ti? You make S an absorbing state, calculate the first passage time from I to S, then the recurrence time from S to S, mean recurrence time, can be calculated using this formula, okay. So, these are useful in calculating, you know, these expected mean recurrence time, the expected time to capture in these kind of problems, and you can work out several examples along these lines, right. So, this concludes my discussion of short term behavior. Thank you.